Hello. Okay. Welcome back. We continue with the second morning session. Professor, please.
Thank you. First, I have to correct myself because I was reading my own writing. This is typical for presentations which you attempt to make spontaneous. You make terrible mistakes. One of the terrible mistakes is that I just put the Apostel theorem the other way around. So I'm sure you got the message, but if you read that, take photos, please correct. I have to correct myself because this is just the other way around. I was suggesting that a quantized system in that state, which is not orthogonal, can have a definite classical value, which is terribly and utterly wrong. You know? So just the other way around. Then no has or can have. So sorry for that. You know, the meaning was that nothing that is perpendicular or collinear can be negative. Yeah? Is it? I'm sorry for this, but I was just writing the text up, and I was confusing it. So no, yeah. And it's hidden. I mean, this theorem is hidden in the Apostel paper in the Journal of Mathematical Physics, and it's not hidden in our paper because it's our main theorem.
Sorry. Okay. The statement is then no. It's a universal statement, yeah. No blah blah blah. The Spectre theorem is existential in some sense. Just gives you.
Yeah. This is much. Well, this is. The Cauchy-Spectre theorem says, I give you a certain set, so certainly not all.
Exactly. You know? Yeah, I show you that this is not the case, and I show you the example. That's why I told you it's constructive.
And they say, yeah, but this is also constructive. Then if you say, well, you don't like the no, you know, which contains a lot of uncomputable vectors, you know. Actually, in the Lebedev sense, most of these vectors are uncomputable because their components are part of the continuum, and I just need one component to make it uncomputable to the degree that you will raise your hairs, you know. But, so I can say, would you be more satisfied with them? There exists one observable. And the one observable is
okay.
And the one observable is this one.
Good. And here, in that case, contracted because you give me the.
But my claim is that you give me some, let's say, constructive. Now you're a computer scientist, recursion theorist. One has to be very careful with recursion theorists. You know, you give me some, you know, which needs to be constructive. Otherwise, you wouldn't be able to give me. Or you would grab one out of the back of the continuum with the axiom of choice. Yeah, then I cannot. If you use the axiom of choice, this is not highly non-constructive. But as long as you produce something computable, I produce something computable. I produce an algorithm which would give you something.
Yeah. Excuse me. Isn't it also true that no non-commuting set of projectors can have such a classical assignment?
Yes.
It's almost equivalent. That if the set of projector is may not commute to each other, then you won't have this assignment.
Then I won't have it. Yeah. But he was. I think he was. You know, this is the. I observed it this way because this is. You know, I give a course. The theoreticians usually look down at the experimentalists, but the experimentalists, but the theoreticians are looked down upon by the mathematical, and the mathematical physicists are looked down upon the mathematicians, and the logicians sometimes look down upon the mathematicians. So this is
it's a pecking order.
Yeah, it's a pecking order. but of course, they are right. All of them are correct in a certain sense of their framework. So, but of course, the logicians and the logicians, they are basically the recursive functions. They use recursive function theory as an excuse to do logic. So this is my impression I get from those guys. So he was alluding to the fact that this is a how should I say, a minefield, you know, a recursion theoretic minefield. Because once you bring up the question of computability, you enter some kinds of things which are interesting, but needs to be taken care of, because the assumption of the continuum implies that you bring in back almost all elements of the continuum are not only non-computable, but they are random, that is algorithmically incompressible. I think we, yeah, okay. So Axis 1 is okay, and this one is constructive, and whenever you present me one computable, I will give you a computable proof for that. And if you allow me for uncomputable proof methods, I will give you a proof for uncomputable numbers. But then it's not constructive any longer. Okay. So with this caveat, I hope I'm really sorry for this misformulation. Let's then go to partition logics. I'm talking about partition logics because with a student a long time ago, I created automaton logic based on the Moore paper. So the Moore paper is A.F. Moore. I've forgotten how the title of the paper was, but it's something like automaton uncertainties. And I tried to build a propositional calculus based on Moore's models, actually on Mealy machines. Mealy machines have the property, if you allow me to give a heuristic description, that everything is deterministic. There's a finite number of states. Everything is finite also. That is, deterministic means that it's a total function. Everything is finite, has a number of finite states, a number of finite input symbols, a number of finite output symbols, and the transition function in particular is defined as a total function which would map a given state with a given input into a definite output state. And the output function is obviously a total function which would map the state and the input into an output. So you have presented, and then the question is the following, and this is the question Moore posed, basically. I present you a black box and I tell you there is a Moore automaton in it, and I give you the entire structure of the Moore automaton. You know, its internal workings. But what I don't give you is the state it is in. So we are talking about state identification problems. So I present you with a Moore Mealy automaton, and I tell you can input something, and this produces some output. Here's the input, which is also symbolic. And I give you the entire specification of the automaton, this finite automaton, but I don't specify which state I chose this automaton to be in. And your question is to find by experimentation in which state it is in. And then, quite expectedly and more constructed in the way explicitly to perform like this is that if the transition rules are many to one, it might occur that you can ask certain questions, but then you're dead. You cannot ask other questions. You cannot analyze the whole possibilities of this automaton being in some state. Because I will give you an example in a minute. It will be very clear. So basically, if you ask it a question, it will give you some answer, and then it will transit into something that you cannot ask it any longer. It's unrelated to its previous state. And this was what we were interested in a long time ago. This was in the 80s. And then I discovered that somebody else has done, somebody else meaning Wright, John Wright, he has done some analysis. Wright is the person who invented this exotic measure on the pentagon. He has done some work on generalized Uhr models. And the generalized Uhr models are like this. You have an Uhr, and you have balls on the Uhr which are black. And then, this is just one example. And then you have certain symbols in color. And in another color. And you are supposed to put on eyeglasses which are either blue or which are either one color or the other, and they need to be of complementary color. So when you put on, let's say, the green eyeglasses, you wouldn't be able to see the red symbol because it meshes with the black background. Yeah, I mean, for all practical purposes, this doesn't work in physical experiments, but this is how the mathematicians think physics works. So, or how the theoreticians assume it works. So, and vice versa. If you put on the red eyeglass, you don't see the green symbols. Meshing with the black background. So you have your choices. You can measure the red observable or the green. If you measure the green observable, you don't know which ball type it is, you know, because if you observe one, it could still be the ball type with a red one or the ball type with a red two, and vice versa. So this is a model of complementarity. Yeah. So I discovered that this is and then I discovered that these models are equivalent with respect to structure, to logic, and the equivalence, and the logic behind all this is partition logic. Actually, we had partition logic before, and then I realized that this announced the partition logic. So these are two models, two physical quasi-classical realizations of the same thing, and all of them, and I will give you the automaton model realization in a second, both of them have the property that you are able to model complementarity, but we're still talking about a system which is totally classical in the sense that there exists some, even if you cannot observe it with your glasses, there exists some reality behind. That's the ball type, you know, you're taking up. This may not be true any longer in quantum mechanics, and the Kolsch-Becker type or Titowski or ours arguments say that quantum mechanics is different because there doesn't exist the two-value measure. And all of these models from a measure theoretic perspective, all of these models are characterized by the fact that, according to the Cauchy-Specker theorem 0 in their famous paper, all of them have a logic which is non-Boolean and which may be non-Boolean and in particular, non-distributive, but which have a sufficient number of two-valued states such that always you can separate the balls from each other or the states from each other. And the automaton model I give you now, I invented in the Viennese subway because I'm going to the subway as in Santiago. There's also good subway system, so I go with the Viennese subway and sometimes I sit down and in Santiago, you know, nowadays everywhere in Vienna and Santiago, everybody looks into his or her little screen, you know. But at that point, I'm already that old that I had invented that when I had no screen available. So the screen was too tired to look into. So I assume that there are three states. I just give you the subway automaton, Mili automaton example I developed in the Vienna subway. There are three states labeled 1, 2, 3. And everything is deterministic, and then I have to give you the transition function and the output function. And usually what in automaton theory, in Mili theory, people do is they draw arrows indicating the transition function, and they draw a slash indicating the output function. So, this consists of three states, labeled 1, 2, 3, and 3 input and 2 output symbols. The input symbols for convenience are also labeled 1, 2, 3. So, whenever it is in any state and I input a 2, it makes a transit into 2. And if I guess correctly, so if I put 2 and it is in 2, it remains in 2. And says you guessed correctly and it gives me a 1. Yeah, okay? So far, if I guessed incorrectly, if I guessed the state incorrectly, it makes the transit into 2. So here is the many to 1. Yes? And output 0. From 2 also, from 1 also to 0. Okay? You see, here already at this level, you see that an interesting feature. If I guessed incorrectly, I'm dead after one question because it is in 2 and I cannot ask it any longer. I know it that it is in 2. But I cannot tell you whether it was in 1 or 3. I can differentiate between 2 and the rest, but the rest isn't enough. It doesn't resolve the entire set of internal states. Yeah, and correspondingly the other ones, 3, 1, this gives 3, 0, this gives 1, 0, and this gives 1, 0. Yeah? It's very symmetric. Now, what we figured out is Martin Schaller and myself. Martin Schaller now works in he was one of the most ingenious students I had in my life, you know, Martin Schaller. Extremely bright from a formal point of view, and I'm very happy that he developed this with me. So Charlotte and I mean, I had the he formalized it in a mathematical sense, but the idea came in. It was a cooperation. Let's say this. I usually think when I hike, or when I listen to concerts. And this was on a hike, and I still remember the hike when I had this idea, this partition idea. I hiked to Furt in Wienerwald. That's a very nice place where you have waterfalls and even some photos. But this was a long time ago. Okay, so if you input, let's say you input 1, and I look into the respective. So in a sense, the idea is that your input-output analysis gives you a resolution of the entire set of two-valued states. Yeah. And by the way, Chaitin, do you know Chaitin? His first paper was on the Moore paper. Chaitin. Yes. His first paper was, if you look into his publications, it's funny, he was still working in New York from the New York Library there. So he does, I asked him once and I said, what about this? He said, oh, that is long time ago, not seen, But he was interested in that. Not in the particular problem in physics, but in the state identification. It was a hot topic at that time. Okay. So if you input a 1, of course, you may output, you may get the output 1, or you may get the output 0. And depending on your output, you can say whether it's in state 1, if you get the output 1, or that it's state 2 or 3. Yeah? So this gives you a partition of this state. And then you are dead. I mean, you can... of course, there exist automata where you have to ask a second time and so on. But this is not so much of an issue here. So and it's symmetric. If I input a 2, I will be able to differentiate between 2 and the rest. And the rest is 1 and 3. And if I input a 3, I can differentiate between 1 and the rest. And Moore's idea was that you get a kind of uncertainty because you have to decide what you input. Yeah? And depending on the input, you have this observable, which you can resolve, or this observable, or this. And you are dead afterwards. So this is it, You have to choice. But this is not resolving the entire thing. So this he calls automaton uncertainty.
Regarding 3 shouldn't be 1, 2.
This is again, in on the table, same thing. I'm sorry for that. You should not trust me anyway, but in particular not when I write something on the whiteboard. But this is good because I teach methods of theoretical physics, and the students know that I sometimes make mistakes, so they hunt for mistakes, Yeah. So they say, "Oh, I saw a mistake," and I said, "Yes, happy." That keeps them alive during the lecture. No mistakes. Okay. And you may ask now, well, but what is the logic? What is the logic now? And I'm giving you now the Hasse diagram. The Hasse diagram represents the relation in a not so compact way as the Grigio diagram. The Grigio diagram is easy. The Grigio diagram is just 3, not connected. You know, 1, 2, 3, 2, 1, 2. No, 2, 1, 3, and 3. Be careful now. 1, 2. Yeah. So this is the Grecian diagram because this channel and what the next idea then is that every such partition, and I call it partition logic the big thing, you know? I combine all these partitions and I consider now the elements of this partition logic and I consider that as a Boolean subalgebra. And this is a concept that is well known in quantum logic. They call it pasting construction. Pasting construction. So they all fall asleep when you mention pasting construction, but it was an active research area. For instance, in Kalmbach's book on quantum logic, it's heavily used, and Vrije used it heavily, this pasting thing, and it's very well described in a paper by Mirko Navarra. But this is for the mathematicians. The pasting construction in quantum logic. Mirko Navarra, somewhere in the 1980 or 90. Okay, so what is pasting? I identified this with the Boolean subalgebra, and I draw the Hasse diagram now. The Hasse diagram contains 0 at this element and 1 here and 2, 3 here. And here it says 1, 2, 3, and I kindly ask you to interpret this as 2 or 3, and this 1 and this and, yeah? 1 and 2 or 3 goes to the impossible, or 1 or 2 or 3 goes to the tautology. So this is a Hasse diagram now. And of course, you get similar constructions. Let's say with 2, 1, 3. It gets boring now probably. And the interesting thing is that these are together. 1, 2, 3. Now the Hasse diagram, the pasting construction identifies identical elements on all these subalgebras. So this one would correspond to what they call a Chinese lantern type Hasse diagram, because it looks like a Chinese lantern. So there's a 1 here and there's the not 1 here. The not 1 equals to 2 or 3. And there's a 2 here and there's a not 2 here, which equals to 1 or 3. And there's a 3 here and a not 3, which equals to 1 or 2. And here is 1, 2, 3. Here's the common element which are pasted, where they are interconnected. Now this is a disjoint pasting, but there exist much more elaborate structures where you have also at the non-trivial, at the non-extreme ends of this relation, you have also identifications, and you have to do that. And this, by the way, is a famous physics experiment. It's spin state measurement or polarization measurement, two-dimensional thing. But it's not, they cannot be connected, they cannot be connected at these levels here, at the intermediate levels, because this is a two-state thing. But still it demonstrates the capacity. Now, of course, quantum logic is much more, because you have all kinds, this is a continuum, in quantum logic. You can measure the spin along a continuum of directions. If you really can do that, that's certainly, because this is non-constructive. And how can you construct a non-constructive? This matter let aside, if you assume a Hilbert space, the Hilbert logic is much stronger. Here it's just 3 Boolean subalgebras. This is the first one, this is the second one, and this is the third one, pasted together at the extreme ends. And yeah, so in order for the generalized Ullmann model, you have a particular color, a distinct color for all subalgebras. You need, for all subalgebras, for every single subalgebra, you need a distinct color. And then you can also go on wild. You know? I think, let me figure out this. So if you have let me give you the ball types. How many ball types are there? I think there are 8 ball types. This is ad hoc. Now let me just 1, 2. Let me just try to get you a feeling for, given a particular logic, what kind of partition logic, what partition logic maps what kind of partition logic realizes that logic, and then go progress to the coloring scheme. The general idea behind this is that if you get a quantum cloud, let's say if you get this quantum cloud again, yeah, this has 5 two-valued states, as I said yesterday, and 5 two-valued states. I will just mark the ones there. Yeah, and you have those. Yeah. So, what kind of partitions? What kind of partition logic? Realizes that structure. And the idea is to use the two-valued states, because you still have value definiteness everywhere, and you can use these extreme cases of two-valued states to map a particular graph structure into a partition logic, to find a partition logic. As long as there are enough two-valued states, that is, as long as the two-valued states are separating according to 0 and 0 of quotient spectra. And well, if you label this the first, the second, the third, the fourth, and the fifth measure, you can find the partition logic according to this. This element, you ask yourself, when does this element acquire the value 1 on which two-valued measure? In this case, the way I draw it, it acquires it at the second measure, so you do a kind of inverse construction of the two-valued measures, and the third. This element acquires it at the fourth and fifth. And this element acquires it at the first. And then this element acquires it at the second and the fifth. And First, this is then requires it at the third and the fourth. So you have, if you bundle those elements together, this needs to be all because all two-valued measures are covered. Of course, if I miss a two-valued measure, I cannot do that. But these need to become distinct just by the rule of two-valued measures. So this is the intuition behind it. So you get two partitions, 4 for this element and 1 for this element and 2, 3 and 4, 5, and you get the partition 1 and 2, 5 and 4, 3. And mind you, this is the same construction that would give you all the classical probabilities. Because if you do a complex combination and say, well, here's the lambda I, which must sum up to 1, and lambda I should be, since it's a complex combination, bigger than 0 or equal to 0 and smaller or equal to 1. Then you get, for instance, lambda 4 plus lambda 5, and here you get lambda 2 plus lambda 3. So this is a very compact, and here you get lambda 1. So this, by the way, just gives you all the possibilities of generating Urban model in a certain sense. Yeah. So this gives you all the classical probabilities. And it is an alternative model, an alternative. It presents these partition logics present an alternative representation in a totally different model than the quantum one. I mean, we have obtained this from the quantum theory, but this has a different classical interpretation, and this is new. One can look into all kinds of partition logics now, and some of them don't correspond to quantum logics. Some of them are weird. So this is one way of doing this. And the second, let me just try to explain to you what I mean. How for instance, which kind of generalized Urban model would correspond to this? Yeah? And I give you just an example. The Bartz, who is a proof theorist in Austria, very early on mentioned that the Babylonians used proof techniques which were very different from ours. It's in Neugebauer, mentioned in Neugebauer's book, saying that the Babylonians, if they have a theorem like this Gaussian theorem to sum up all natural numbers and how, they would prove these theorems by inserting large numbers. And this came out to be correct. They would say this is a valid proof, which reflects a little bit to what Specker has said, because Specker in his later life was very much into zero knowledge proofs. And in a sense, this is zero knowledge for the Babylonians. So, okay, I think it's good sometimes, for me as a physicist, sometimes I'm more convinced of a good example than of the full proof, because the full proof is so involved that I don't understand it, but if I see a reasonable example, I say, hey, I like it, So for instance, my students in Vienna, I prove the spectral theorem for non-degenerate spectra, This is easy, and even I can present that in a reasonable style. But the students are more convinced when I show them explicit decompositions, such that I would solve the characteristic equation and get out the eigenvalues, and then from that I would get out the eigenvectors, and from the eigenvectors forming the orthogonal projections, and then expanding that beautifully, and someone say, "Oh my God, this is very impressive." So in a sense, I understand that people want examples, and I think you had also this give me examples, and I will give you an example how I would try to create a generalized good model for this one. And in order to do that, I need all the two-valued measures encoded into that partition logic. So I need the partition logic. Yeah, the partition logic I get from a given graph by all two-valued measures. Okay. So I need as many colors as I have partitions in these answers, and I have, let's say, I identify this with the color red, and this with the color green. And then I say, well, I make a green one here and a green 2 here, then I just sum it up. And here it makes a green 3. And here I make a red one. And here I make a red 2. And here I make a red 3. Now, I make a red one here and a green one here, because this is just a dash. Then I make a red 2 here and a green 2 and a green 2. But I need as many balls. I need a red 2 here. Just a second. And for the third one, I also need a red 2. And here I have a green 2, and for the fifth 1, 2, 3, 4, 5. The other ones I don't need, because I need as many ball types as there are two-valued measures. 2 and 5. This gives 2, and I put that. And here I need for 4 and 5, I put a 3 here according to these rules. And then I have to just make up 2 and 5 and 4 and 3. 3 and 3. Yeah? So I get 5 ball types, which I throw in that room. And go into that room. And whenever I measure, I put on the eyeglass and see a 1, I can be sure that this is also a green one. Yeah? But whenever I measure a 2, I cannot be sure whether it's this type or this type. Yeah? Or a 3, this type, and vice versa for the green type. So if you, your labeling now, the labeling that corresponds to this corresponds also to the labeling of the two-valued states. So this is 1, 2, 3, 4, 5. So you get you don't know when you measure a 2 whether this is ball type 2 or ball type 3. Or a green 3 whether this is ball type 3 and 4. This maps everything into the correct structure. So this is a constructive, not only constructive but positive forward way of generating from a given set of 2 value states which are separate, non-separate, which are separating a particular Wood model, and I have not shown you this with the automaton, but it's the same. We can construct automata doing the same thing. So let me give you, I'm not sure how long have we got. How long still have we got? Well, anyway, I give you one example. We have done this house example, this pentagon example. And I show you how this method of 2 value states gives you partition logics, but also gives you predictions, which are called now Piaget-type inequalities. But may I say, this presents a way to construct non-classical models which feature complementarity, but which are still value definite. So I couldn't construct anything like the last diagram with this model, because if no 2 value measures exist with that method, I fail completely. I can also not do the gamma 3 of co-change beta, because it's also not separate. So I couldn't do the combo configuration. Let me be a little bit more artistic for my do this. This is a context and this is a context intertwined here. I couldn't do this because this doesn't separate this and this or this and this. I couldn't do that. But I could do the combo, and I could do the extended combo. This is a TIF and this is a TIT. I could do that. This is one. Should probably, it's better to write it that way. This is the TIT. And this is the, because this contains still a lot of states, 2 value states, which are both of them, which are separate. But I cannot do this. So this is too tightly connected for any set of 2 value states. But it contains a lot of 2 value states, but they are just not separate. So the set of 2 value states couldn't resolve this structure, but could resolve the other two. So I think it's a nice way. And I've, by the way, at some point I got a little bit. In Vienna, they have this demonstration of quantum cryptography. And of course, the BB84 protocol, Bennett-Poisson protocol of 84, BB84 protocol, it's a nice protocol, but it has cryptanalytic possibilities which they mention in their original paper. But this is what the reviews don't mention so prominently. They also mention it. I mean, I found it in in the U.S.A. Rev Modfuls, it's a small passage. It's larger in the original paper. It says active eavesdropping. With active eavesdropping, they mean that it can be cryptanalytically attacked by man-in-the-middle attacks. Not if you are in the middle of the quantum channel. You have to possess both channels. You know, but the issue is this. They start out by saying, well, this is an advantage over classical because the classical channel might be compromised. So I need authentication, classical authentication to establish that there is no eavesdropper because the classical channel is unsafe. And then they need the uncompromised classical channel. But from the outside they assume that this can be compromised. So on purpose they fix an uncompromised classical channel and do the, I will explain that to you if you are interested also. And this is contained. This Bennett and Poisson accepted that. They call it. It's I think 2 or 3 times it's mentioned. The term active eavesdropping. It doesn't say man in the middle. It says active eavesdropping in the original BB84 paper. So it can be cryptanalyzed. And my idea was because there was this, in Vienna, you know, everybody was talking about BB84 and how secure it is. And I said, well, let's then do an attack on cryptography by man in the middle, you know, by attacking both, you know. And I asked that, of course, those groups who did the first experiment, which were prominently, they didn't like these ideas. So I went to, it is very difficult to do single, I mean, there's never a single photon in the field. You know? This is one thing they seldom mention, but it's of course standard knowledge. You always have many photons, and therefore this is also a cryptanalytic thing you have to cope with. And they pretend to cope with it. But it is very expensive, so I couldn't make it out of the box. It's a typical situation. Physicists, theoretical physicists invent something, experimentalists don't believe that this is important. So Bennett did his own experiment, but he was at IBM, you know. And he did his own experiment, and in the own experiment you see this little classical channel, I believe, even, you know, swept under the carpet, which is not compromised. It directly goes from Alice to Bob. And I said, well, let's do an attack, first attack in Vienna on quantum cryptography. You know? Nowadays, many people have done it, not in Vienna. And I failed miserably because I couldn't get the equipment. And nobody gave me the equipment. So what I did was, I kind of jokingly invented a BB84 type protocol with chocolate balls. Because Vienna has a big production of chocolate balls. You know? And they gave me, my son at this time was 10 years old. They were happy, and my daughter, because they fetched some remaining chocolate balls. I got 2,000 chocolate balls. And I did this by mimicking complementarity with chocolate balls. So it's an American Journal of Physics article, which then I'm honored to say that Professor Prasad, so one of the DP, not Bennett but Prasad, said, "Oh, I used your chocolate ball model to teach the Canadian Parliament Club members the BB84 protocol, you know." But he didn't do it with chocolate balls. In Canada, he did do it with eggs because it was a breakfast meal. Of course, I mean, it's also interesting to see the difference, because the difference is that the quanta, they are, well, this is a quantum system in 2 dimensions, so it can be still, but the quanta are, everybody believes that they are value indefinite, you know? So whereas in a chocolate ball you just need to get off the eyeglasses and you see the definiteness of everything. You see the whole glory. This whale of Salinger likes to call it, this whale of the quantum of Maya cannot put anything off. You cannot look at all the observers because it's very definite by these Kirchhoff-Becker kind of constructions. If you believe in them. So. I mean, if you believe in the assumptions and the implications, and if you are not an idealist. So it has some deficiencies. This has some deficiencies over the quantum, of course, because otherwise you could really do cryptography. And NSA just buys a lot of, we would be happy, you know, NSA buying a lot of Viennese chocolate balls. Or probably they buy only American-made chocolate balls just because of this Huawei thing, you know. The Viennese could put some little things to, you know, to report to the Austrian government, you know. One never knows what Mana does. Okay, so let's not go into these details here, but let's just say so. So this was one way of doing this, and I will now give you an example which is very popular now in the quantum physics community, which is this pentagram logic or the house logic I was mentioning yesterday, and I gave you already all these 11 two-value measures. I'm sorry to be so pretentious and write this up again. But as Feynman said, one never should underestimate the joy one has by doing something one already knows. So I will just draw, I won't draw the exotic one, just the standard two-value measures. So let's start here, and here, and here, and here, and here, and here. And then you go on like this, this, and this, and this, and this, and then you have this here, and this, and this, and this here, and this. And this, and then go on to the next. This is simply, it's the same all over. This and this, this, and this, and this. Last thing is this, and this, and this, and this, and what have we got here? And here. And the final one is center pieces only. This is cute. This is more symmetric. Okay.
You have repetitions.
Huh?
You have repetitions.
Do I?
No.
No.
Yeah. The fourth and the 10th.
1, 2, 3, 4.
And
the fourth and the 10th?
Yeah.
Thank you.
You should have all 10
Yes,
pairs.
no,
10 pairs.
Yeah.
And the opposite.
Yes. Just a second. I have this here, and then why did yeah, I have this here, and then I use this, and this, so the pens is
The fourth is not on the intersection, it's the middle. It's the middle. So very close enough. No. That the red pointer is in the middle bar. It's in the middle of the bar. Not in the intersection of the two.
But
It's not in the intertwined axis.
let's see, I have this.
That's on the intertwined axis, the other is not.
No, but you must have only
No,
one
so
point.
I think this is okay. this here. So this one must be wrong. I have this here, and then I get this and this. Somewhere at the back. So this is okay, I think.
The vertical pair is missing, the left vertical.
The left
Vertical pair.
yeah, the left vertical. So I make so I have this here, and then I need that to be here, and I think I can use this one here, which is okay, but then I need this here. So the force is okay, I think. Let us write 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So the problem is with this one. I certainly have this here.
But the vertical left pair is still missing.
The vertical,
You cannot do both nodes to the left, one above the other.
But this is a value measure. So what is missing here? Probably I first have these, then I have those, then I have those, then I go on with this one.
I mean this, you have red.
Yes.
This one is missing, I think.
When
And you
I,
have, instead of this one, instead of this.
could you?
It seems to me that this one is missing.
This one is missing. No, this one is not. This can't be.
It's not allowed.
It's not allowed. It's not allowed. That's interesting. So we got a problem, and we will solve that. We will sort that out. We will sort that out. Probably I made a mistake. Let's just be cautious. Here it's okay, I think. We are still okay. Then I go on with that. I go on with that in a cyclic fashion. I have always this, and then I have 2 of this, and then I have 2 of this, and 2 of this. Yeah? So, when this, I can have this here, but then I need this. And you rightly say
4 and 10 are equal.
4 and 10 are equal.
But also 2 and 5 are equal.
2 and 5 are equal.
Yeah, of course.
So 2 and 5 are equal. Yes, yes, yes. So I made a mistake. So let's identify the ones that are equal and add the other ones that I missed, because I surely must have missed them. You know? So thank you. So 2 and 5 are identity. So yeah.
Because
Yeah, you're
if
right.
you take all possible pairs,
No.
then you have 10 plus 1, 11.
No, I'm sure that they are 11. I'm quite probably I'm wrong. So this one is 10. I have also not identified, and probably there's still 2 more pairs. Let's 7 and.
But you said there were not allowed. So
No, I just draw an empty one. So let's see if the force and
because
do you see more identity?
you have 10 possible pairs of nodes taken out of.
Yeah, but you see, I can I can still, what I still can do is I can do this, this, and this, and this.
That's good. Yeah.
And then I can do, see, this is why I'm searching for a certain.
You can have 4.
Yeah, and then I can do this one, this, and this. Okay, that's also okay. So I'm searching for one more because I could do a lot of more. You know, I can do this. This and this, okay. And then I can do this, and this. And I can do finally this, and this. Okay? Yeah. So I have more. Unless there are identical ones. Let's see. Identical ones. So see here, this is identical to 7. Yeah. So I erase that and write 7 on this one here. And let's see if I get more twins, identity twins. If I have this, and this, yeah? This is identical.
Yes.
So I get a 9 here. And I just need one more twin. Please help me. You know, this is a typical case where one learns from one's own mistakes. So, but I'm quite confident that my argument still goes through because I've done it so often that I can present you even a page. You know, you see, you know, it's so easy. So where is the second twin? This no. Here this is wrong. I got it all wrong. Because this is allowed. So I have to. So I got all kinds of mistakes. I'm really sorry for that. But this is basically, I hope this is basically the set of 2 mistakes.
But number 10 you can rotate. I think you have rotated versions of number 10.
Yeah. I mean, this is rotated. This is all rotated, and it's in a wrong numbering scheme now. But let's. I can. This is a permutation. I can permute that. That's not so. Okay. So I think I'm done with this. I hope I got everything. Yeah. Okay. So let's then turn to the. Let's then turn to just this intertwining vertices. Let's put our attention to the intertwining vertices. Okay. Draw a big house now. A pentagon or pentagram, it's all identity, subject to a permutation. And look at the 2 valued measures that are one at those intertwines, and don't care about the other ones because they just add up to give a partition of the rest of 1 to 11. No? So here I get the 1, 2, and let me be brief and not make the brackets. You know, 1, 2, and that's it. Here I get a 3, 4. That's it. Here on this one I get a 2 and 6. Here I get a 9 and a 1. And here I get that is a 6. a 4 and a 6. Okay?
But just one question. Your set should be closed under symmetries of the pentagon. Is that true?
Maybe. I cannot answer your question. This is too complicated for me at the moment. Please don't give me this. I have to say, I am already struggling with that.
The only thing I wonder is why you're putting 4 dots in 9 and 7. Shouldn't be only 3?
No, because I need.
Can be 4?
I need, yeah, because I mean, I could get rid of those if I would make those. I could get rid of 2 if I make this right.
Yeah, okay.
But this would be somewhere contained in
yeah,
here.
it's okay.
Yeah. So I need to get all. It must be exhaustive. Usually I don't do this. I mean, I've done this manually. For the Pentagon, it's impossible, as you see. But if this is huge, I just go to Cutler's program and change the program instead. So, but what is important here is, if you look, these are classical predictions, you know, and you know from the classical predictions that all classical predictions from 1 to 11, lambda I should give you a 1, with lambda I again satisfying these conditions. No, 0. And I'm getting there somewhere because I have lambda 1 plus lambda 2 here, and I have a lambda 3 plus lambda 4 here, and I have a lambda 2 plus lambda 6 here. Lambda 1 plus lambda 9, lambda 4 plus lambda 6, because this directly translates. So if I add them together, I get two 2's here. I get 2 4's here.
But just 1.
I get 2 1's here and 2 6's. And just lambda 9 and the lambda 3, so I get lambda 3 plus lambda 9 plus 2 times lambda 1 plus lambda 4 I'm sorry, plus lambda 6. Did I forget anything? No. This is smaller than or equal to 2 times lambda I from 1 to 11. This is 1, so this is equal to 2. And this is what is called the stairs path inequality, which they use to give you a proof of this can't be classical if this set is, if these probabilities here are just taken into account in what they call failed state measurements. So this is a direct, if you interpret them classically, and you have all the classical interpretations here. I'm sorry for my wrongdoings, but we all corrected them together. These are classical interpretations. This gives you a kind of, I mean, I could give you the full, or if you look at my papers, this gives you the full partition logic. You know, you can have generalized Wooden models from that, automaton models, but I'm only interested in these lambdas here, in the classical probabilities, and the classical probabilities gives you classical prediction that if you sum up all these intertwined, the probabilities on the intertwined observables, this shouldn't exceed 2. In quantum mechanics, I can give you configurations where those probabilities with some preparation state gives you larger than 2. And this is one instance, not really in the spirit of Bell, because in the spirit of Bell you need to develop the correlation polynomial, but it's more in the spirit of this TIFS thing, where you prepare something and this should be 0, you know. But yeah, it's considered to be a Boole-Bell type inequality, but it is derived just in this very simple way of interpreting it classically. And it's violated by quantum mechanics. This is a quite recent publication by Stairs and Papp.
There are some missing numbers, but they don't modify the inequality.
They must miss because all of them.
5, 8, 10.
All of them. Let me give you this link here. You know, this link is
You have lambda 5.
you have
8.
1 and 9 here, and here you have, I think we did that already, 2 and 6. So this thing here should be the rest. You know. So when is this? This is 4. No, I have 3 here. I'm sorry.
At the top one?
See, I missed one here. I missed one here.
At the
I
top
got another
is
3.
5 also.
So I get to
You
get
have a
this
5 there.
2. Yeah. So
9.
I have here in 9 1 with 3. 1, 3. Where's the 9? The 9 is here. Yeah, 1, 3, 9. Here I have, let's repeat that, a 2, a 6, and a 7. Oh, I missed the 7.
Yeah.
Okay. 7. So I have to add here the plus 7. Lambda 7. Yeah, but it's okay because it's still
It works.
yeah.
Anyway.
So I get a 7 here, and here I get a 4, a 5. I better get the rest, you know? A 4, a 5, an 8, and an 11. So this adds up to 1, 2, 3, 4, 5, 6, 7, 8, 9, where's the 10? I missed the 10. 10 is here. Must be in here. 10, 11, and that's it. So the partition is 1, 2, 3. No, 1, 3, 9. 4, 5, 8, 10, 11, and 2, 6, 7. And you always better check it that you really get all of them. Because if you haven't gotten, you have most likely either drawn as I did, the 2-unit measures wrongly, or you didn't take all the 2-unit measures. And this is true for all of them. You know, all of them get a different partition. And if you bundle them together, you paste them together, you get the partition logic. And this has also some usefulness, as I said, for physical predictions, because this is violated by quantum mechanics, this classical prediction. That's a very compact way of deriving it, believe me. There exists less compact ways. So, yeah, I'll probably show you a partition logic which has no quantum correspondent. This is probably my last work on that. And in a certain sense, you know, I have a long time talked about this, even before, you know, I was I did a lot of things, including psychoanalysis, and I also went to the film academy, and I like to watch movies. Every science fiction crap you can give me, I watch. You know? Because I like science fiction. This is why I like to go to the stars and so on. So in particular, this is no crush, of course. I like the Matrix. But long before the Matrix, I have given a talk what if we would be living in a computer-generated universe. And the grandson of Boltzmann, Professor Flamm, sat down in anger and said, this was in Vienna, and said, now Svozil has completely got crazy. And I was already on the crazy guy's side, you know, so this just, and Shimanovic, who was preparing the manuscript, he said, but Svozil is the only one who got the manuscript ready for preparation before his talk. So it didn't say it was good manuscript, but he has prepared it. So this thing keeps remembering. So what really, if you would be living in a computer, you know, there's a famous paper, not famous, it's the paper by Toffoli saying that, and of course Wolfram, you know, and all these guys, which was, and Zeilinger introduced me, because it was, Zeilinger came back from MIT, and this was very, very posh at MIT at that time. You know, everybody was talking about this. It's Fred King, you know, Toffoli and so on. And I still like it. I mean, so everybody, we were talking about what if the world would be a machine, you know, and in a sense, those automaton uncertainty relations give you some answer, because you would experience the world, you would experience complementarity, you know, in a very similar fashion. So you would do all these spin state measurements, and you would believe that this is quantum mechanics, you know, because this is automata, consequence of automata. It's like universal computation. Of course, everything that you could do with universal computation, if the machine is sufficiently involved enough to support piano arithmetic, which I assume is universal. In the Turing sense, it should be universal. It will do, and it will also do the trick with complementarity, because this is how it is, you know. But it will do something more. So far I have told you that automaton logic or partition logic could not do the same thing as quantum with these diagrams called Specker. But quantum can also not do certain things that automaton logic can do for you. And one of these things is a triangle in 3D.
Just a question and a comment. What is the relation with this automaton with the interpretation of Toff, Gerard Toff, about quantum mechanics? Toff.
Tooft is very much into, first of all, Tooft isn't interested in this stuff, because Tooft is interested in, at the basic level, cellular automata.
Okay, yeah. But
he's famous enough so that he wouldn't take notice of me, because the entire thing I told you, nobody cares, you know. Nobody cares at all, which is an advantage because I have my little field, you know. But it's a disadvantage because you would feel that this is important, and then somebody comes up and confuses value indefiniteness with complementarity, which is ruled out by my model, you know, because it doesn't know that there exists something in between, some possibilities. But as I said yesterday, if you don't point your fingers to an experiment, they don't listen. And I mean, this is a potential experiment, but you don't tell them how to do it, so they won't listen either. It is quite justified. So in a sense, this is only very theoretical, and Tooft is a Nobel laureate and has his own program, I believe, which I find justified, but he's very much into going into one direction. So one could say with Mahler, my time will come, but probably it will never come. Most likely the situation is the following, that some new guy who is famous will come up and pushes this, markets it under a new name, and then, it's like the Alexandrov theorem of incidence geometry. Alexandrov, this is the Russian fate anyway. They have this somewhere hidden somewhere a long time ago, and then some German and American mathematician comes and reinvents it. It has happened to Alexander, it has happened to many people often. So this cannot be, because it's too tightly connected. In 3D you cannot have this. Because once you can do this, but you cannot interconnect these any longer, just because of geometric reasons. You cannot, if you have tripod and you shift that, you cannot connect this with the original ones, because this would coincide. It's impossible to do it. Well, I won't prove it now, but this is undoable here. This has no faithful orthogonal representation in the sense of Novak, Wegener, and Schrift. But it has, you can figure out a partition logic and a generalized Pool model by just, I don't know now how many, so I just draw a lot of these. So let's figure that out. This and that, this and that, this and that, and then you can have this, and I think then you're finished, aren't you? It's just 4. More two-valued measures you can have. Because if I have 2, here this is disallowed. I cannot do it. So basically 1, 2, 3, 4. So basically the partition logic is this. It's 1. Here you get 3, 4. Here you get 2. Here you get 1, 4. Here you get 3. That you get 3. And here you get 2 and then it has its little guessing with the lambdas. This is just a shorthand for the lambda. You can have your automata and your generalized group model, but it has no correspondence in quantum mechanics. And of course there exist other ones. These ones, I've given a soup. They are very weird looking things. Like you can have, as long as it's, you can have this one, or this one, or this one. All things that you cannot do because it has no faithful orthogonal representation. I have written up a paper on that. And Cabello was very interested in the weird, in the wild things. This is funny that he didn't look into other things because.
What's a paper when you talk about this?
This was a recent paper last year, and probably if there will be a proceeding, I might just take my chances and submit it. Okay. But it's in archive. It's in archive. I will show you the soup, and then I will. Oh, it says Sim Semyar. Here. Like this. Yeah, okay. So, I think. Oh, no. I'm not interested in that one. Worlds pointer. My homepage again. This is starter. And here I have the publication list. And here I got the preprints. And it's quite, yeah, for partition logic. Here it is. And it will, you know, here is a more systematic way of, with the numbering more systematic than I did. But so the SU is here. Here is the SU. So you can have more tight pentagon, and we can go wide. I constructed all types just for the fun. But this is, you know, this is really derivative work from something I did long time ago. I actually did it. The problem is the vocabulary, you know, because I did this because Capello said, because you can have faithful, but he has these rules. In Capello, I was just proving that non-quantum structures can do the same job. Then many things he said can do quantum mechanics only. This was mine. Probably I'm certainly interpreting him incorrectly, but I was just giving an example because many people claim now that this is the weirdness of quantum mechanics. You can have those things. You can have many weirdnesses already on a quasi-classical level. And I'm not, you know, and there's one thing that let me finally point out the following thing. Now, we have learned that, for instance, the pentagon has a classical interpretation and interpretation in quantum mechanics. So you get an algebraic structure from those logics, which have at least two interpretations in terms of probabilities. Now that already implies that the algebra itself, I mean, from a mathematical point of view, that appears to be trivial, I guess, doesn't force you to accept a certain kind of probability. You know, the simple algebraic structure. So, because I just got you two which are consistent and obey those Kolmogorovian axioms within co-measurable things, because here these are co-measurable. Yeah? So the question arises, isn't there a more general probability theory on the horizon who would do just that? Who would give you all the possible probabilities, not just the quantum and the classical ones, on such structures, but which are more exotic. And with the pentagon, the right example is a good indication that yes, they exist. But such a theory doesn't exist. And and nobody listens. So I ask constantly, and nobody listens. So at some point I said, well, I probably have to figure it out myself, but I haven't so far. We just need a functional class which would add up to 1 on the co-measurable ones and would be different from the trigonometric class associated with quantum mechanics and from the convex combinations, linear convex combinations associated with density. So is that unresolved problem? I leave you.
So your vision, I mean, in the long term, is that this would have some this kind of effect?
If we would be living in a computer-generated universe, there would show up some structures like that. Yeah. This is my problem, because I cannot point to any.
Could you show the first page? of your
Yeah, but you just need to Google my name, then you will be on my homepage and you can do the same as I did. Just look at the publication list. Yeah, I was, at that time, since I was working with Adrian Capello, I got a lot of input from him. And I'm really thankful for that. And he knows a lot that I didn't know. So he knew about the faithful orthogonal representation thing. Somebody probably told him, but I wasn't aware of that. So it's totally reasonable to speculate, to ask if you have an automaton partition logic which you can graph theoretically represent, does this have a faithful orthogonal representation? And well, I kind of asked this I kind of asked Jose Bartillo, because he was working, and I said, you are the expert in faithful orthogonal representation. And he just said, well, that's an interesting question, which is a very reasonable answer. And in order to motivate people who are willing to think about that, like U.S.A, he's visiting me now in Vienna, doing this, I wrote this up because I had no other thing to do. This was in spring last year. I was swimming in the Danube Canal. I like to swim, It is easy in Vienna. If the weather is fine, it's easy from the TU to go to the swimming place because it's free. You can just, there's a canal, which used to be, if the Danube is high, which it never is, they open up the gates, but all the other time everybody enjoys himself in 2 times 11 kilometers beach. So I was swimming and doing this, I still can remember that, doing this. But as Thomas is here now, really, I think there are many questions, but the most important question for me would be, given such structures, such kind of structures, are there more exotic? Give me, please, a complete theory of all the probability distributions. Classical, quasi-classical, or quantum, yes, but more. I want more. That work on these structures, such that on every context the Kolmogorovian axioms are satisfied. So this is still I think a very vital question.
It is a fact that there are many classes, many types of structures, right? There's the classical, quantum, some others, and some others in between as well. The classical and the dimensional beyond the quantum.
Yes.
What you are asking for is a sort of characterization of what would determine to be one class or another.
Yeah,
from the logic.
This is one sub.
Because you can also discover a new one and another one and another one. Because you never know if it's going to end.
I don't think, no, let me say.
So for the case of computational complexity, for example, you have a very clear description of what is a complexity class. Because you determine in terms of function, the order that it will take compared to the size of the problem.
But it's clear, but it's clear, but it's, as the computer scientists tell me, it's unclear.
Yeah, there are questions.
Because is NP in polynomial time? I mean,
so that doesn't deny the fact that there is a characterization. Now that the questions within this characterization can be answered or not, it's the very top.
I mean the question is that, it's a little bit similar. You're absolutely right, because you might say, because if NP complete turns out to be in B, then those classes collapse and you got one class.
Yeah.
So, but the question I'm asking here is, given a certain type of structure of diagrams, let's say allowing only those diagrams allowing a non-separating set of 2 valued states, a separating set. That would be basically, I believe, just the partition logic. what kind of probabilities can I get on those? Or the other question is, if I add more, if I enlarge the class to also allow non-separating, what do I get then? I certainly wouldn't get quantum mechanics because I would have this here. This is disallowed in quantum mechanics. So, and the Pentagon tells you tells you that there is more to it. So.
Have you heard of the descriptive complexity? Descriptive complexity?
No.
Which
Yes,
is something that relates logical, let's say, systems to complexity classes.
No, I have probably not.
I'll show you.
Yeah.
Because it will be, maybe this is something like quantum computation and complexity. Something like from the logics we can go to the complexity
But
classes.
it's not this Bennett logical depth. It's not, because Bennett has this notion of logical depth.
Yeah.
It combines.
But it's not from that side. It's coming from the computer scientists.
Yeah. Yeah. Well.
Yeah, no, but it's yeah. Interesting. So.
But I think I'm finished with this topic.
Done? Okay.
Yeah.
But sorry, the probability theories you are thinking of, they all boil down to a partition of unity, or not necessarily?
Yes.
In some sense, it's just a partition of unity.
Yes. 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 Yes.
Because you also have some non-commutative versions.
Yes, no, maybe, but this, I mean, maybe, yeah, it all boils down, you're absolutely right, because on all those contexts, they should add up to unity. So you can say, well, the question solved is just the partition of unity. But there are certain classes which might be interesting to sort out. And then the question is,
related with
this would be a typical IELTS question. Can you build really models of that in real, which would correspond to non-classical, non-quantum, but weirder or different? So this is just a question into this. If this can be extended somehow.
And don't you see any relationship with the random walks in these structures? Such a random walk may generate a probability, which is not the usual thing.
I have no intuition, but I would say if you start out with some quantum, as long as it's computationally universal, maybe in the Turing sense. And this is another thing, just as a reminder. I spent two semesters with a very good recursion theorist, Alexander Leitch in Vienna, figuring out the quantum computation claim that they can do universal computation. What they actually prove is they can do Boolean logic, is this. But not universal computation in the Turing sense. So they are confusing. So this is good as dissertation.
Did you write something about that? Can you point?
Chris wrote, because first time I mentioned this to Chris, he didn't know this. Second time,
Chris,
he wrote some, and I pushed him, and then he wrote it down. He has a recent paper on that. But yeah, I think the reasoning is quite. But I forgot how he did it. So because we were, this was the constant question. Hey, they are doing these gates, but gates is typically first order logic. But you need second order. Where's the second order? Where's the self-reference? You know, where you have substitution and turning the code into programs and think of yourself, self-expressibility, and then you get into problem. Not with these U.S.A gates. U.S.A gates you just push through and that's it. So my challenge to those guys is tell me the gates who would encode the Ackermann function. And of course, the Alexander Leitch tells me, well, yes, I can do that if I have an arbitrary number of gates. So I use this function, but this function comes from where? Then your president of the institute comes in, but you have to use some input. It's like quantum computation. It's like quantum communication. You said, but there is this active eavesdropping, the man in the middle attack. This is not quantum computing is not immune to that, and quantum communication. And then they said, yes, of course you have, but so we just grow the key with BB84. An existing key. What do they mean? They have to use classical authentication to do quantum communication. That's the truth. The DARPA network in Boston just works with classical authentication, which they use as a seed, and they claim they can grow the seed. But this is entirely different from the claims you hear from that community. Okay.
So,
thank you.
We finished the morning session. We will take the